For my Math 321 final project, I am modeling the total human population growth over 100 years for a game called Worldbox. As you can see, I have 4 kingdoms, all starting with 10 people, and the terrain is pretty similar, as well as the world laws. To minimize all of the sudden disasters and other random deaths to keep the population growth as simple as possible. Um, what I did for the tracking is, you can see over here on the spreadsheet, I just used the speed up option for the time, and I tracked each population and paused it at 1 year time steps so that we get a total of 100 years um, for each kingdom. And then I set up the spreadsheet to calculate the total human population at each time step, which I will then use later on to graph and for the necessary information needed for the initial value problem for the differential equation, which we will talk about in a little bit. As you can see from the differences in the growths, uh, it is also quite variable, which is why using the total population also helps. It just simplifies things even more, um, not having to deal with all these different variable growths. Moving on to the differential equation, we have a pretty common one. dp over dt is equal to k times p. What we're trying to do is isolate this p-value and get a nice simple equation. First thing we did was we divided by p and then multiplied by dt to get this. And then we took the integral of both sides. And then afterwards, we took the exponential of both sides to get rid of the natural log, which gives us this. And as you can see, we have a c. So what we did was we know that the um, initial value is equal to p at time step 0. So we just replace that with the c. And then we also know that our initial value is equal to 40 because of the 4 kingdoms, which each have 10 humans in it, which gives us this equation, which is a p of t is equal to 40 times e kt. And the next step is to find the k value. First things first, we know that at the last time step of 99, our total human population is 1385. So we just put that in and then replace the t-value with 99. And for solving for k, we just divide by 40, take the natural log to get rid of the exponential, and then divide by 99 to isolate k, which equals this weird random fraction, which is roughly equal to 0.0358, which gives us the last equation that we need to plot, which is p of t is equal to 40 times e to the 0.0358t. And after plotting it alongside our population growth to total population growth, we get this. As you can see, it's roughly exponential growth, and as such, the IVP doesn't exactly match it, but it does fit pretty well for populations later down the line. Overall, though, the IVP was pretty simple and it was quite effective in uh, matching our population growth that we talked about, and is pretty consistent with first order approximations that we used earlier in this class. Thank you for watching.